as the complexity of systems grows, we find that the bus architectures that were described so far and that are typically used are no longer really practical, or rather lead to problems that make it harder and harder to be solved using the existing techniques, which is why we move on to another concept called a network on chip. Okay? So we are not going to go deep into networks on chip. The idea is just to sort of get a flavor for what can be implemented using the technique. In particular, we will not be implementing any of them as part of the assignments or the project. It's up to you. If you want to do it for your project, that's fine, but we will not be covering that as far as the course itself is concerned. Alright, so the first thing is one aspect of bus architectures that we need to understand better is the concept of DMA, direct memory access, right? Now, why do we need DMA? The basic idea is that in any given system, normally the structure that you have looks something like this. You have a bus, you have multiple masters connected to it. Typically, those masters would be CPUs. There is also some memory, and there are peripherals, right? So now, especially with a peripheral like Ethernet or some other kind of high-speed interface, what ends up happening is that the amount of data that that peripheral needs is considerable. It's very large. Okay? It can almost get to the point, if you're talking about gigabit Ethernet, you might be getting close to the point where if you really want to continuously feed it data, the processor, one of the CPUs has to be busy on every clock cycle, just getting data out of memory and feeding it to the Ethernet interface, right? Not quite at that much, because the actual CPU to memory bandwidth is usually an order of magnitude or more higher than what Ethernet can handle, but still it gets to the point where it becomes appreciable. The CPU is going to spend so much time transferring data that cuts into the useful work that it can do, right? So here a new kind of master, a bus master, is introduced called a DMA unit, right? The idea of DMA is it's a direct memory access. That's all it does. It cannot do processing, it cannot even add two numbers together, right? But on the other hand, it specializes in the task of taking data from one location in memory and transferring it to another location in memory. And as long as we are using this concept of memory mapped peripherals, that's perfect, because any two locations in memory correspond either to actual physical memory or to a peripheral. Okay? So if I want to transfer data from memory, which is sitting in a buffer in memory, into, let's say, the Ethernet port, the processor then has to do the following. It has to set up the DMA peripheral, right? Meaning that it has to give it some instruction saying, take X amount of data and transfer it from address location A1 to address location A2. Okay? So whatever words are there from A1 to A1 plus X, take those data and transfer them to address locations A2 to A2 plus X. Okay? There is an instruction in the C programming language called memcopy, which you may be familiar with. It's used for bulk copying of data, right? DMA helps with precisely this kind of situation. Effectively what it does is, what people realized is, during a mem copy, when you are copying data from one place to another, the CPU is not really doing anything useful. It's not doing arithmetic, it's not doing any logical comparisons, it's not deciding where to branch, right? So why not just have another unit that can take care of this kind of transfer? Now, why it is useful is because the DMA unit by itself is not capable of doing anything else, which means it's a simple unit compared to the CPU. But on the other hand, it takes the load off the CPU and allows the CPU to concentrate on other tasks. Okay? What this means is, this has to act both as a slave and as a master, right? Why a slave? So that it can get instructions from a CPU, and a master so that it can take control of the bus. It needs to send out bus requests, get the bus grant signal from the arbiter, and initiate transfers, right? A read request from one memory location and a write request to another memory location. Now, especially in the past, one very popular approach was something called cycle stealing DMA, where literally what the DMA unit would do is, if I told it to transfer, let's say, 1 kilobyte of data, it would wait for a while, wait until it would basically put out a bus request, and the moment it gets the grant, transfer 1 or 2 very small number of bytes and immediately release the grant. Okay? Why? Because if you don't do that, then the CPU is going to get blocked until you have transferred all 1000 bytes, and you can't afford to do that, right? Then the CPU takes over, the CPU then goes, chugs along, does some work. The moment it releases the bus, it's no longer doing a memory operation. Because the request from the DMA was always high, it will get the next grant, again transfer some data, release it after a short while, and so on. Nowadays this is not so common because especially with pipelined transfers and so on, it becomes hard to really predict exactly when you can take control of the bus, when you can release the bus, and so on. So you don't really see this term used very often, but the principle behind it is that the DMA unit is sitting in the background and only doing work whenever the CPU is not actively working. Another thing that can be done with DMA is something called scatter gather, right? So effectively what you can do is, scatter essentially says, let's say I have one incoming source of data, like an Ethernet port. Okay, there is always one address from which I am reading data, one location from which I am reading data. But if I try writing that always into the same destination location, after some time the CPU, the operating system, may not have had time to pull that data out and process it. So I need to actually spread this data around multiple buffers. Okay, so the OS can basically create a large number of buffer spaces and give it to the DMA and say, okay, use these buffers. Those buffers could be in different areas of memory, but the DMA unit just needs to be given their locations, and it can automatically take the data coming from the source and scatter it to all of those. The reverse can also be done. So the CPU can basically take care of whatever program you are writing. Let's say that you have a web server that's trying to transfer some data. It reads data from a file and puts it into a large number of buffers all around in the memory. And then finally, in order to convert it into Ethernet packets and send them out, it basically does a gather DMA transfer, where the DMA basically gathers data from multiple locations and sends them out to a single port. Okay? So all of these are the different variants of DMA. For our immediate purposes, the main thing that you would need to keep in mind is, for your projects, you will notice that the AXI Lite interface, which was part of the demo, the FFT code that I used for the demo, is painfully slow. Right? We saw in the demo that the data transfer ended up taking 10 times as many cycles as the actual computation. Right? So the data transfer, out of the total of some 35K cycles or so, or 40K cycles, the data transfer accounted for about 35K. Right? Nearly 90% of the time was spent in that. That's because the AXI Lite is not using DMA and is not managing to get a throughput of 1 data word per cycle. Whereas by using DMA, you can actually improve those speeds to that point. But using it is more complex. It can be done. That's part of what you will need to do in order to really get some benefits in the projects that you are doing. Okay. All right. Now, this all raises one interesting question. Like I said, the DMA unit is being seen as something that has that should do some work, but whenever a CPU wants access to the bus, the DMA should sort of give it to the bus, give it to the CPU, okay? Which means that there is some concept of priority associated with the different masters on the bus, right? And you can sort of intuitively understand that. The whole idea over here is, if I have multiple masters trying to talk to a set of peripherals, supposing 2 of them want to talk at the same time, which one gets preference, okay? And in particular, I might have a situation where there should be some master that always should get absolute preference. Anytime it wants to talk on the bus, fine, just stop everything else and give it. Okay? Multiple questions come up as a result of this. What if there was a peripheral that was using the bus and a new master comes and says, I want the bus? Should I stop that other master and give access to the new one? Or should I wait until this is completed before giving access? Is there a possibility I can deadlock? Deadlock meaning that everybody is waiting for someone else and nobody is able to do any work if such things happen, right? All those possibilities are there. Very similar considerations hold even in the concept of general network access, right? So if any of you have done a course on communication networks, you would know that very similar ideas hold over there. for that matter in the parallel processing systems when you are trying to schedule multiple tasks, similar kind of considerations will hold, right. In other words, this concept of priority, when two people are asking for something at a given time, who gets the access, right, is something that needs to be sorted out properly. So there are multiple ways by which this can be done. After all, the arbitration itself is done by that bus arbiter. Okay, so as long as I can give it some notion of priority, it can decide if two masters request at the same time, which one gets access to the bus. But then comes the question, how do I decide which master has higher priority? One way of doing it, the most obvious one, is so-called static priority assignment. Right? The idea behind static priority assignment is trivial. CPU number 0 gets the highest priority. Let's say I have a scale of 1 to 10, okay? I give 10 to CPU 0. What about CPU 1? Ideally, in a symmetric multiprocessor system, CPU 1 should also have a priority of 10. Both should have exactly the same access to the bus, okay? But a DMA could probably be given a lower priority, maybe 8 or 9, something like that, right? If there was some other master that only occasionally needs access to the bus, give it even lower priority, okay? So static priority assignment can be done, but then it's up to the person designing the system to sort of decide those priorities and assign them. You may not always get it right. We'll see an example of how this can go wrong shortly. There are other methods. Another one that we will look at briefly is something called time division multiple access, right? Once again, for those of you who are familiar with communication networks, you would realize that many of the terms over here would also have been seen in the area of communication networks, because ultimately the problem is exactly the same. There is one resource and multiple users trying to gain access to it. You need multiple access. You need to solve the multiple access problem, okay? And there is some priority assignment, time division, code division is also used, right? Now the CDMA that I mentioned over here is code division multiple access. It is actually quite popular in the area of communications. It has been proposed in the context of on-chip buses, but essentially, I mean, it's more of a theoretical construct. Nobody has really used it in practice. There is something else called a lottery approach, which basically says, at any given point in time, the arbiter will generate a random number and decide who gets priority, right? It has its benefits. It basically makes sure that you don't have a problem of starvation, okay? So let's look a little bit more detail into what are possible problems with priority assignments, right? So this is an example. This chart is basically courtesy of Professor Anand Raghunathan from Purdue. It's some analysis that they had done on a 4-processor system, right? This is basically a simulation, right? Now let's say that you have 4 processors, C1 to C4, and you are assigning static priorities to them, okay? With the priorities basically having this meaning that 4 is high and 1 is low. So 4 is highest priority, 1 is lowest priority. Now what we are assuming is that there are 4 masters, C1 to C4, and also that there are 4 slaves on the system, and that these masters are generating random traffic, right? Randomly they want access to any one of the 4 slaves, and further we make the assumption that the masters are capable of generating enough traffic to saturate the bus if required, okay? One way of thinking about this would be C1 to C4 need to transfer a very large number of bytes from their individual processor, or rather are generating data that needs to get written into 4 slaves. So they are not generating data at regular intervals, they already have the data available to them. So anytime that the bus is free, they can write the next data, okay? So if I had only one CPU active, C1 let's say, right, then essentially what would happen is that C1 would always have access to the bus and it would get 100% bandwidth utilization. Maybe not 100%, for one simple reason, we are assuming random traffic. So the implicit assumption because of that is that at any given point in time, there could be small gaps. After I have generated one packet of data and sent it, there might be some gap before the next one comes, okay? Under those conditions, if I have static priority assignments, right, this is roughly how the distribution of bandwidth looks like. So let's just look at this particular example. The first case, the priority assignments are 1, 2, 3, 4, So in other words, C1 has priority 1, C2 has priority 2, C3 has priority 3, and C4 has priority 4. So C4 has the highest priority, and as you can see, ends up getting almost all of the bus. Okay? Well, or rather, C4 is able to transfer a large amount of data. How is C3 getting into the picture? You remember those gaps that I told you? Whenever there is a gap, if there is an outstanding request already waiting from C3, it's immediately given to 3. Okay? C2 gets access only in those rare cases when neither C4 nor C3 is currently asking for something. So already the bandwidth that C2 is getting is much lower, and C1 is essentially starved. Starved meaning literally, it's not getting any access to the bus, right? This is called bandwidth starvation. Okay? Now what happens if I change the priorities 1, 2, 4, 3? You can see that now C3, the orange bar over here, has priority 4 and C4 has priority 3. The relative bandwidths that they get switch around. Okay? The exact details over here don't matter. What is obvious and sort of clear from this picture is that for any possible static assignment, at least one of the processors will get completely starved, right, very badly starved. Another one will have pretty poor bandwidth share, and the other two will basically hog all the bandwidth. That's when you have 4. Okay, if you have more of them, the situation will be somewhat similar. At least you would definitely have some that are starving and some that are hogging all the bandwidth. Okay? So in other words, static priority assignment has this problem, right, that if all the masters on a heavily loaded bus, in other words, that is when all the masters are trying to generate large amounts of data, there is a very severe problem of unfairness. Okay? An alternative that is proposed is to use something called time division multiple access, right? So let me just briefly say what time division multiple access is. In the idea of time division multiple access, I am going to say that I will take my time interval and break it into slots. Okay? And at any given point in time, at any given slot, right, I will basically say, okay, during this slot, C1 or C2 or C3 or C4 is allowed to communicate. Right? So one sort of degenerate case of this is I always say C1, C2, C3, C4, then C1, C2, C3, C4, etc. There is another term that is usually used for this kind of allotment. What is it? Round robin. Okay? So this is the so-called round robin allotment. Essentially what it is saying is that all the masters that could potentially be asking for the bus, I will allocate a static time slot for them. Okay? Now this is great because effectively what it means is that every master is guaranteed a certain fraction of the bus, in this case 1/4 of the bus. Right? Now what happens if I know that, for example, all 4 masters don't require equal priority or do not have the same amount of bandwidth requirement. How could I extend the same idea to handle such a situation? I use the same time slots. Right? But now what I can do is I will say that slot C1, the first 3 slots are given to C1, next slot is given to C2, next 2 slots are given to C3, and next 3 slots are given to C4. Okay? Effectively what it means is that I am now going to divide up the bandwidth in the ratio 3:1:2:3. Okay? So in other words, C1 will get 33% bus bandwidth, C2 will get effectively 1/3 of that, so 11%, C3 22% and C4 33%. Obviously point something so that it all adds up to 100%, right? But effectively, if I know in advance that this is roughly the bandwidth share that they need, then this is a great way of scheduling, right? Because all that it says is everyone is guaranteed to get their amount of bandwidth, right? It's decided ahead of time. So any given, as far as the bus implementation is concerned, it becomes very simple, right? The bus doesn't even need to actually look for request signals. It just has one small counter and switches assignment after so many cycles, okay? Of course, it has a problem. The problem comes about because of this, because let's say that I'm reserving slots, right? And I had a situation like this where this first slot, which is basically over here 6 clock cycles, right, corresponds to master 1, okay? And let's say that master 1 initialized, or rather did a bus request at this point in time, okay? That's great, because what happens is that immediately 1 clock cycle later I get access to the bus. And let's say similarly that master 2 requested over here, it also gets access 1 cycle later, master 3 requests over here and gets access 1 cycle later, and so on. So the waiting period is basically 1 in this case. This is of course an ideal situation where everyone is accessing or requesting access to the bus exactly 1 cycle before they need it or before they will get it, and also that it's periodic requests that are coming in, okay? Not completely unrealistic, it's entirely possible that you can have situations of the sort, especially in real-time systems, because there are repetitive periodic tasks that happen there. The problem with this approach obviously is, what if the request from master 1 came at this point, right, just as it is going to lose access to the bus? In the very next cycle, master 1 has lost access and master 2 has got access. How long does it have to wait? It has to wait for 13 cycles before it gets access to the bus, okay? In other words, it starts becoming somewhat sensitive to the time when a particular master requests access to the bus, the periodicity with which they request access to the bus, how much of a slot, how long is the slot duration that has been given to each master, right? All those issues can have impacts on the latency. In other words, this can potentially lead to high latency, right? But as far as the fairness is concerned, it is a much fairer distribution of bandwidth than the original static priority based system.